In the last section, we have derived the kinetic model of the CPM controller, right? So here the blue curve, blue chalk indicates the canonical model expression, and the red chalk indicates that it is the specific coefficients for the buck boost CPM controller. So now let's try to analyze the transfer function of the CPM. So we can use still use the buck boost example, CPM buck boost example. So there are three key transfer functions, right? One is the control to output. So CPM, control to output. So based on the canonical model, we can first derive the expression, right, for GVC. So GVC is defined as the ratio between the output voltage and controlling signal. For here is the controlling current, right? So defined as output voltage divided by IC. And given the condition that the line input is 0, only one small signal disturbance. So according to the blue chalk indicators, right, we can see that it's pretty easy to derive from the control to the output, right? So if the VG is 0, then this current source will be open circuit. So the output voltage will be only affected by the independent current source. So the output voltage will be just equal to this F2 times IC times the impedance of C parallel with R over D, right? So it's easy to solve. So the result is F2 times parallel of those three impedance, R2 parallel with C parallel with R. And specifically for buck boost example, we insert those coefficients to replace F2 and R2, right? So we can find out the expression. I will use the red chalk. So here is minus 1 over the fraction of D prime over 1 plus D times the fraction that 1 minus S times DL over input voltage minus output voltage divided by 1 plus S times RC over 1 plus D. So now let's look at the resulting formula for the CPM control to output buck boost example. So we can see that this is indeed one single pole, right? One single pole, and one right half plane 0 performance. So one pole and one right half plane 0 behavior, right? So in retrospect, now let's retrospect what is the control to output transfer function for pulse width modulated buck boost, right? So we can do the comparison. For PWM buck boost, so we have derived the control to output. For PWM, the control is duty cycle, so GVD, right? GVD. And the result is that minus Vg minus V over d square, d prime square, times the fraction of 1 minus s times Li over Vg minus V divided by 1 plus s times L over d prime square R plus s square LC d prime square. So that's the previous derived pulse width modulated buck boost converter control to output transfer function. So now, if we look at the result, we'll see that this is a single zero, right? Single right-hand plane zero, and a pair of quadratic pole, right? So to compare, we can see that this indicates that CPM it has simpler dynamics. And specifically, one pole, the one inductor pole, is moved to high frequency. Next, let's look at the second transfer function, so which is the line to output transfer function. So CPM, line to output. Based on the blue chalk indicator, so we can first write the canonical expression for connector model, right? G, V, G is defined as the ratio between the output voltage and line input, given the condition that the control input is 0. So now let's look at if the control input is 0, means that here IC is 0. So here is open circuit. The current source is opened. And here is also opened, right? So that this current is G2 times the line input voltage. And output voltage is determined by G2 Vg times the parallel of those three impedances, right? So the result will be G2 times parallel of R2 as 1 over SC and R. So pretty similar to this one. The only difference is the coefficients. Now the output is determined by the transconductance term, G2. So we can also derive its full expression, right? So here is equals to minus d squared over 1 plus 1 minus d squared times 1 over 1 plus SRC divided by 1 plus d. Again, you will see that this is simpler, right? So this is the single pole response. And to compare, for conventional pulse width modulated, we can also review its line to output transfer function for P of M. So I will just give you the result, right? So here is minus d over d prime times 1 over 1 plus s L over d prime square R. See, this is a pair of quadratic pole response. So this argument is still valid. Simpler dynamics, inductor pole is removed to high frequency. And thirdly, we look at the CPM, output impedance transfer function. So for output impedance, we will consider that the line input and the controller input, they are all 0. So here is open, here is also open, right? So, but we have a small signal disturbance in parallel with the load, right? So the load will, the disturbance on the load current will affect the output voltage. So you will see that basically the effective output impedance will just be equal to the parallel of those three impedances. R2 parallel with C, parallel with R. So the expression for buck boost topology will be R over 1 plus C times 1 over 1 plus S RC over 1 plus D. So same, right? Single pole response. Single pole response. And for conventional pulse width modulated, so the out will be equal to the L effective parallel with 1 over SC parallel with R. I will no longer give you the detailed expression for this parallel impedance network, but you can see that there is a L term and a C term. So this means that it's a quadratic pole response, right? But CPM is a single pole response. So this argument is still valid. CPM has simpler dynamics, and inductive pole is pushed to high frequency. So in this section, we utilize the example of the buck boost converter to derive the transfer function of the CPM controller. By comparing the CPM transfer function and the conventional pulse width modulated transfer function, we can see that the CPM pushed the inductor-induced pole to very high frequency, so that the dynamics are much simpler.